Hey guys, welcome back to another lecture video for Chem 115. In this lecture video, we will continue our discussion of Le Chatelier's principle by taking a look at how changes in temperature will affect the position of the equilibrium for a given chemical reaction. To begin, I want to review the three common indications that will inform the reader whether or not a chemical reaction is undergoing an exothermic process or an endothermic process. And so the first clue that I want to discuss is the potential energy diagram, which is something that we covered in greater detail in kinetics. So let's just say that you guys were given a chemical equation on an exam that's coupled with a potential energy diagram. And so based on your knowledge of it, you should be able to discern whether or not the chemical reaction is either exothermic or endothermic. And so one quick way to do this is looking at the position of the potential energy of the reactants with respect to the position of the potential energy of the products. And so it doesn't matter if this is a one-step process or if it's a two-step process or a three-step process and so forth and so forth. If we simply take a look at the potential energy of the reactants and the potential energy of the products, that will more precisely tell us whether or not it's an exo or endothermic reaction. And so in this scenario, if the potential energy of the products is much less than the potential energy of the reactants, then overall, the process is exothermic, meaning that heat is going to be released from the system to the surrounding. For an endothermic reaction, the potential energy of the products is much greater than the potential energy of the reactants. And so this would be the scenario in which the reaction is going to be endothermic. In other words, there is no net release of energy. Rather, there's going to be a net gain in energy from the surrounding into the system. And so another clue that would indicate to the reader whether or not the reaction is exo or endothermic is the sign of enthalpy. So let's just say that you guys were given a chemical equation on an exam, and the only thing that is given to you is the value for enthalpy. And so I don't want you guys to focus too much on the actual value, rather the sign of that number. And so if the sign of enthalpy is negative, then it's telling you that the reaction is exothermic. Once again, heat is being released from the system to the surrounding. For endothermic reactions, once again, we don't really care about the actual number, we just care about the sign. And so if the sign is positive for enthalpy, then the reaction is going to be endothermic. And so the last clue that I want to briefly discuss is more or less a physical clue. Like, what would an exothermic or endothermic reaction feel like? And so I want you guys to think about a combustion reaction. And the most benign combustion reaction is the burning of candle wax. And so if you guys are lighting a candle, for instance, the heat is being released to the surrounding. And so if you guys were to put your hand close to the candle, you would interpret that sensation as something that's warm or hot, depending on how close you get to the flame. And so if the reaction is warm to the touch, or for example, the reaction is aqueous and it's inside a beaker, and then you feel the beaker and it's warm to the touch, then that's an example of an exothermic reaction. So for endothermic reactions, it would be the opposite, meaning it would be cold to the touch. So an example would be an ice cube. And so if you guys can do this at home, but if you guys were to, put your finger on an ice cube, then remember that the reaction is absorbing energy from the surrounding. And so your finger would be the surrounding, since the system is the ice itself. And so since the ice is absorbing energy from your finger, right, so heat is going into the ice cube that will allow it to melt, you're going to physically interpret that as something that you're touching something cold. Okay. So that's pretty much a quick review on the 3 different clues that can signal the reader to determine whether or not a reaction is exothermic or endothermic. Now, how does all of this play into Le Chatelier's principle? And so it turns out we can go ahead and treat heat as either a reactant or a product. And so looking at an exothermic reaction, remember that for exothermic reaction, heat is being released. And so in a chemical equation, we can represent an exothermic reaction with heat being placed on the side of the products. In a similar manner, heat for endothermic reactions, since there's going to be a net gain, energy is being absorbed, it's going to go to the side of the reactants. And so when you guys are applying Le Chatelier's principle with respect to change in temperature for exothermic or endothermic reactions, you guys have to follow 3 steps. And if you guys kind of skip these steps or just do your own thing, it might lead you to the wrong conclusion. And so for you to be able to predict how the equilibrium will shift with changes in temperatures for exothermic or endothermic reaction, the first step is to determine if the reaction is exothermic or endothermic. So for this example, I want you guys to note that the sign is negative. So this is a clue, right? So here, since the sign is negative, then this is telling us that the reaction is exothermic. Great. So now that we know it's an exothermic reaction, the next step is to represent the reaction, the exo or endothermic process, in a chemical reaction. In other words, we're going to substitute this with heat either placed on the product side or heat being placed on the reactant side. And so since this is an exothermic process, we're going to go ahead and represent heat in one of 2 ways in the chemical equation. We can put heat, we can literally just write the word heat, or we can use the symbol for enthalpy to represent heat. And so I'm just going to go ahead and highlight exothermic just to be consistent with this example. So once you guys have represented heat on the correct side of a chemical equation, then and only then can you apply the actual change in temperature by either increasing or decreasing heat or enthalpy. And so if you treat heat as, for instance, a reactant or product, then increasing the temperature or decreasing the temperature will allow us to predict how the equilibrium will shift. So what do I mean by this? Okay. So in this scenario, notice that we're going to increase the temperature for an exothermic reaction. And so this would be how we would represent that the reaction is exothermic, by replacing that negative delta H to writing delta H on the product side. And so since we're increasing temperature, that means that we are, let me see if I can, do I have more room? Yeah. So if I am increasing the temperature of the system, that means I am adding heat into the system. Well, if delta H represents heat, and if we treat heat as either a reactant or a product, in this case it's a product because it's exothermic, then adding heat increases the concentration of quote unquote heat. And if you guys recall from a couple of lecture videos, that when you increase the concentration of a product, Le Chatelier's principle tells us that we're going to have to consume what was added, and therefore the equilibrium will shift in the it will shift in the opposite direction. And so here in this case, since we added heat, it's going to shift to the left. So here we're going to add heat, therefore Le Chatelier's principle tells us that the equilibrium will shift to the left. So what is this telling us? This is telling us that for equilibrium to be restored, we need to consume the amount of heat added. And the only way to consume the heat added is to allow the two products to make more reactants. So when the chemical reaction has reached its new equilibrium, there should be more reactants than there are products. So there is an overall shift in the position at the equilibrium, favoring the production of reactants. Okay. So hopefully that made sense. So we're going to go ahead and look at 3 more scenarios. So the first scenario was an increase in temperature for exothermic reactions. And so we're going to go ahead and look at the scenario where we see a decrease in temperature. So decrease in temperature for exothermic reactions. And so I'm just going to go ahead and just kind of talk out the steps. And so the first step is to identify whether or not the reaction is exo or endothermic. And so if I look at the sign for enthalpy, I see that it's negative, so therefore it's exothermic. And so I'm going to go ahead and represent exothermic in the chemical equation by writing either delta H or heat on the side of the product. And so now that I know that heat is a product, then I'm going to go ahead and apply the change in temperature. So here I have a decrease in temperature. And so I'm going to go ahead and apply the change in temperature. And so in this case, there's going to be a decrease in temp. And so if there's a decrease in temperature, then that's telling us that we're taking away heat from the chemical reaction. Okay. And so what we're doing is essentially decreasing the concentration. I'm putting concentration in quotes because we're kind of treating heat as if it was a product. So we're decreasing the concentration of heat. Okay. And so what does Le Chatelier's principle tell us? And so if we decrease the concentration of a product to counteract that disturbance in equilibrium, then the equilibrium will shift in favor of the production of the substance that was lost. And so, in other words, the equilibrium will shift to the right. And so, when the equilibrium is shifting to the right, then that's telling us that to replenish the heat that was lost, because we're decreasing the temperature, we're taking away heat from the reaction. So to replenish the heat that was lost, the reactants must be converted into products, because the conversion of those products will allow heat to be replenished, since the conversion of reactants to products is an exothermic process. Okay. All right, so hopefully that logic makes sense. And so you can only apply the change in temperature after you kind of figured out where heat is going to be positioned in the chemical reaction. And so if you are taking away heat, then the equilibrium will shift in that same direction to replenish the substance or the heat that was lost. All right, so let's go ahead and look at another scenario. This time we're going to increase the temperature for endothermic reactions. And so looking at the sign, notice how it's positive. So I know that this reaction is going to be endothermic. And so looking at this chart for endothermic reactions, heat is going to go on the side of the reactants. So we're treating heat as if it was a reactant. So A plus 2B plus heat is in equilibrium to C and D, which is a product. And so after you guys incorporate heat into your chemical reaction, then you can go ahead and apply the change in temperature. So I'll go ahead and just copy this and then paste it here. So we're going to apply the change in temperature, which in this case is going to be an increase in temperature. And so when you increase the temperature, that basically means that you're adding heat to the system. And so what you're doing is you're increasing the concentration of heat. And according to Le Chatelier's principle, if you're adding more reactant to counteract the disturbance that was made, it's going to act to consume that reactant by shifting the equilibrium to the side of the products. So in this case, the equilibrium will shift to the right. And so overall, this is telling us that an excess of heat, if a reaction is endothermic, the reactants will be converted to product to consume the excess heat that was added to the system. And therefore, the equilibrium will shift to the right. All right, so let's go ahead and look at our last example. So if we decrease the temperature for endothermic reactions, how will the equilibrium shift? Will it shift to the left or will it shift to the right? All right, so to answer this, we first need to identify that the reaction is endothermic, and it is because it's positive. Sign of enthalpy is positive. And so we're going to go ahead and rewrite this balanced chemical equation to include heat as a reactant. So we're treating it as one of the reactants. And so if we apply the change in temperature, which is going to be a decrease in temperature, that basically is informing us that we're taking away heat from the system. And so if we treat heat as if it's a reactant, then what we're doing is we're decreasing its concentration. And so if we decrease the concentration of heat because of being taken away due to a decrease in temperature in the surrounding, then to make up for that loss, the products itself will, some of the products will be converted into the reactants to replenish the heat that was lost to the surrounding due to the decrease in temperature. And so according to Le Chatelier's principle, a decrease in temperature will shift the equilibrium to the right. Or sorry, not right, left. And so by shifting the position of the equilibrium to the left, we're favoring the production of reactants. And the production of the reactants allows heat to be replenished from the breakdown of the products. All right, so what we did is we went over 4 specific scenarios for an increase or decrease in temperature for either an exothermic and endothermic reaction. And so let's go ahead and work through some practice problems. And so here we're looking at the conversion of solid water into liquid water. So basically ice melting or ice freezing, depending on how you guys are looking at this chemical reaction. And so looking at the first question, how will the equilibrium shift when you increase the temperature of the system? Well, first and foremost, I need to look at the sign of my enthalpy value. So this is an enthalpy of formation, which is the same thing as delta H. And there's a whole bunch of ways to represent delta H of formation, delta H of reaction, et cetera. It doesn't really matter. Delta H is delta H. So for this example, this is telling us that this is an endothermic reaction. And so therefore I can rewrite this chemical equation to include heat as a reactant. Remember, endothermic is gaining energy or gaining heat from the surrounding. And so naturally, to convert solid water, which is ice, into liquid water, heat must be absorbed to produce liquid water, which makes sense. And so now what we're going to do is we're going to apply the change in temperature, so we're increasing temperature. And so when we increase temperature, we increase heat. And so that's going to, we're going to go ahead and treat the increase in temperature as an increase in heat. Therefore, the shift in equilibrium will be towards the side of the product. So equilibrium will shift to the right. Okay, and so by adding more heat into the system to adapt to that stress that was applied, more of this water molecule that's solid in state will have to absorb that heat, that excess heat, to reach a new equilibrium. And so therefore more liquid water will be produced. All right, and so what would happen if what would happen to the equilibrium if temperature in this case decreased? And so since we're still dealing with the same chemical reaction, I'm just going to go ahead and, actually, you know what? I'm going to go ahead and copy this whole thing so I don't have to rewrite it again. I'm just going to go ahead and just change some parts here. Okay. And so I'm going to go ahead and erase this, erase that, erase this. Okay. All right, so since we are decreasing the temperature, and we know that it's still an endothermic reaction because the enthalpy doesn't change, we know that heat is going to be treated as a reactant. And so if we decrease the temperature, what we're doing is we're lowering, if we decrease the temperature of the surrounding, we're taking away heat from the system. And so if we're lowering, let me see here, so we're going to decrease heat. Then the equilibrium will shift to the left to replenish the heat that was lost to the surrounding. Okay. And so when we're decreasing the temperature of the surrounding, heat is going to travel from the system to the surrounding. Therefore, the system is going to lose heat. And so when heat is lost, then the product is going to, some of the product is going to be converted to the reactant to replenish the heat that was lost to the surrounding. Therefore, there's an overall shift to the left. All right, so looking at this example here, looking at this second example, notice that the sign of the enthalpy is negative. And so this is telling us that this is an exothermic reaction. And so now that we know it's an exothermic reaction, we're going to go ahead and rewrite the chemical equation to include heat as a product for this specific problem. Okay, let me kind of scoot this over a little bit more to the center. All right, cool. And so now that we've represented the exothermic reaction as heat in the side of the products, we're going to go ahead and apply the change in temperature. And so since we're increasing the temperature of the surrounding, we're basically adding heat to the system. So if we increase the temperature, we're going to add heat to the system. And so we're increasing the concentration of this heat term. And according to Le Chatelier's principle, the equilibrium will shift to the left. And so let's think about this. If we add heat to the system to counteract this disturbance in equilibrium, we need to consume the amount, or we need to consume the substance that was added. And the only way to consume the substance that's added, since heat is a product, is if we consume product to make more reactants. And so at the new equilibrium, there should be more reactants than there are products. So therefore, there's an overall shift in equilibrium favoring the production of reactants. So there's a shift to the left. Okay, and so once again, I'm going to go ahead and just duplicate what I wrote here. And I'm just going to go ahead and erase some stuff. Okay. All right, cool. So this is still the same example, and it's still exothermic, and so therefore heat is written on the product side. This time, instead of increasing the temperature, we're decreasing the temperature. And so if we decrease the temperature of the surrounding, heat is going to escape from the system, which is the chemical reaction, to that of the surrounding. So there's a loss of heat. And so overall, the concentration of heat is going to decrease. And so to replenish the heat that was lost, the equilibrium is going to shift to the right. And so to replenish the heat that was lost due to the decrease in temperature, what this is telling you is that the reactants must be converted to products, because the production of products will allow heat to be produced, therefore replenishing the heat that was lost due to the decrease in temperature. All right, so that's pretty much it for this lecture video. Hopefully you guys understand my thought, my logic, and you guys are able to precisely predict how the equilibrium will shift with respect to changes in temperature in any given chemical reaction. See you guys in the next one.